All right, well, let's kick this one off. So this is, I guess, the fifth video in our hackathon series. We've got Marcus here with us, and this video will be on Codebase review. So we want to look at a couple of our production Mainnet code bases. So Marcus will walk us through the Door and Elpaca Metagraph code bases. And we'll also look at some of the other example code bases that we have available through our Metagraph example repos. A little demonstration of how to install and set those up locally for use in your project. So I guess let's dive right into it. So first off, we've got the example repo set up. So this is at on GitHub, Constellation Lab /Metagraph examples, and this is a repo that contains multiple Metagraph code bases within it, and each one is set up to offer kind of a minimalist application logic that displays one or two features or things that a Metagraph can do, and so these are really great kind of getting started guides where you can jump in and see how some of the logic and features of a Metagraph work without kind of being bogged down by all the logic that you would see within a production application. So you'll have access to do both of those. See the production, the mainnet applications in a little bit here, but we also have these examples as a resource. And so these examples can be installed directly into the Euclid SDK using the Hydra install template CLI command. And that's going to just be a really easy way to get these code bases installed locally properly. It'll install it for you with all dependencies and make sure everything is set up properly. And then you can just get started from there. So some of the concepts that these code bases cover. We'll see custom data types, so how you define custom data types within your application, how you ingest those through a data endpoint, and then how those custom data types are stored within the state of your application. So there's both calculated state and on-chain state. We've covered some of those concepts in previous videos, but we'll be able to kind of see those in action and how you might make use of those different structures. We also cover API integrations. How do you reach out from your code base to external resources and then integrate that information into your own state? Custom reward distribution. So if you have a token and you want to distribute new tokens to wallets through some custom logic, there are examples that cover that as well. And then I think one of the most useful aspects of these code bases is that several of them have front ends that go along with them. So how do you connect a front end UI site to the Metagraph backend and interact with it? And so looking at how to use Stargazer Wallet to sign custom data types and send those to your Metagraph. So what we can do from here is we can take a little kind of look at the repo itself. This is on GitHub, and then afterwards I can show you a little demonstration of how to install and bring up one of the Metagraph examples with a custom UI. So you can find this repo on GitHub, and first we have just sort of a list of the different examples that are available. Some of them here are focusing on currency only apps. So if your application only has a token, doesn't have any data application logic, there's some examples here for you as well. So you could do custom transaction validation. What constitutes a valid token transaction on your network. You can introduce custom logic to define that. Reward distribution, so distributing rewards or minting tokens and you can introduce custom logic there as well based on your needs. We have a then the majority or the rest of the examples here are on data applications. So most of these would have a token and some custom data implementation. So the first we have is we're calling custom NFT implementation. So this is an NFT implementation that's roughly following the ERC 721 standard. This is not a standard recognized specifically by the network, but this concept of NFTs can really be extended to all sorts of custom data types that are recognized on your network, and cross-network standards can follow with that functionality in the future. So definitely a really good example there. That one has a front-end UI integrated with it as well, so you can see kind of the visual aspect of NFTs there. So two more we've got here. So we have a water and energy IoT example. So this is just sort of a basic IoT use case. How do you ingest some basic data from an IoT device and create state around that and handle that stream of data. And then the one that we'll be focusing on here is the voting poll example. So this one I really like because it implements some kind of simple data types, but it's also in the style of a traditional web application. So it sort of clicks and makes sense how you might use the Metagraph as a backend. But it's sort of a basic DAO use case where you can create polls or topics to vote on, and then users are able to vote on those polls using their wallets, and the number of tokens they have in their wallet is the number of votes that they get on that particular topic. So integrates a few different things, custom data, and also the token logic as well. And so this voting poll has a front-end UI that integrates Stargazer Wallet and shows custom data signing. So I think we can, from here, dive into an example. I'll show you how to use the Hydra CLI within Euclid to install the voting poll example. We'll also install the front-end UI and show you how to use Stargazer with it from there. Okay, so what I want to show here is how we can use the Euclid SDK and the tools within it to easily install one of the examples from the Metagraph examples repo. We can run it locally, see it working. In this case, we can also explore a front-end UI associated with it, including Stargazer Wallet integration. So to do that, the first thing I'm going to do first thing that we did here is that we set up a Euclid project. It has standard installation. We set up GitHub token and all the prerequisites. You can see there's nothing in the project directory. So far it's empty. So the first thing that we're going to do is we're going to look at Hydra install template. And first thing we can do is list. So it's going to reach out to that GitHub repo and let us know all the available templates or examples that we can take a look at. And so in this case, what we want to do is install the voting poll example. So this is going to fetch that code from the repo. It's going to add it to our project directory, which you can see here. So that's going to include the Metagraph code and also our front-end UI code in the sample UI directory. It also does a few other things to configure the project for you. It sets up the tessellation version to match what's in the example so that there aren't any sort of tessellation version mismatch issues, which can be a problem with building. It also sets the project name to set this project as default. So when we run Hydra build, it's going to go ahead and build that project. So what I'm going to do now is just go ahead and we're going to run Hydra build and then Hydra start Genesis, and we will come back to see the results of that after a few minutes. Okay, and so we're back. We just ran Hydra build and then Hydra start Genesis. which builds all of our executables and then starts the chain from Genesis, or the very first new snapshot with no old data. So you can see here there's some useful output to the end of start Genesis. We're seeing that we have a Metagraph ID. We're seeing then each of the containers with the URLs to access any of the nodes on that cluster. So for example, we could take a look at the node info for this particular node. That's showing kind of what's going on that node individually. And then there's also the cluster endpoint where we can see what that node sees as the cluster for, in this case, the L0, Metagraph L0. So we see 3 nodes. They're all in ready state. That means our Metagraph is up and running. And so we're in a good position. So the next thing we're going to do is navigate to the sample UI directory here. So that's where our front-end site is located. And we're going to go ahead and install that. So this is just a React project, React.js based project that uses npm. So we're going to run npm install. Oops, looks like we've used the wrong version of Node, so we're just going to redo this here. We're going to use version 20 of Node. Okay, so I'll try npm install again. npm does tend to have a ton of output. Most of it is not useful, but it does look like we're successfully installing here. So that worked properly, and then we can go ahead and run with npm start. So this is going to build and serve our local front-end project here. Okay, so it's going to be served at this URL, which you can go ahead and check out. Great. So we can take a look a little more of the screen here. So we have our site all built and running. I think this error is not particularly important. But this is demonstrating how to use or to create a front end that interacts with the Metagraph, serving as its server backend. So in this case, we have a Metagraph that supports the creation of polls. So these are things that can be voted on in sort of a simple version of like a DAO framework, where you would have individuals vote on particular topics, and they use their wallet to do that. So the first thing that I'm going to do here is go to create poll, which tells me I need to connect my wallet. So I'm going to go ahead and do that. Oh, it looks like mine already came up here because I was already connected, but this is a Stargazer wallet that it will prompt you to connect if you haven't done that before. It's also showing that I have a balance on that wallet already, this kind of crazy number here. And so that is showing up, and I can show you how that's configured here. Within your source directory, Metagraph L0, Genesis, we have this genesis.csv. So genesis.csv is a really important file. It's just a CSV file that has a map of addresses and balances. And those balances are what the network starts at Genesis. So it starts in the very first snapshot with this particular balance map. So you can edit this to whatever you want. You then need to rebuild your project and it will take effect, but you can distribute those initial balances however you want. And one thing to keep in mind is that these values are in what we call datum, or the smallest unit of DAG. And so if you wanted to convert this to a DAG-based unit, you'd move 8 decimal places. So 1, 2, 3, 4, 5, 6, 7, 8. So we can see that this has 19,999 and these decimal points, which matches what we see here. So I've already done this here for the demo, but you would just edit your own Genesis file to have a balance on your wallet, and that way you would have a starting balance. So we can go ahead and create, a quick demo poll here. It's just a really basic form. So we're going to do option 1, option 2, and option 3. So in this example, the polls are only valid for a range of snapshot ordinals. So this is sort of a way of telling time. So we can see in the upper corner here, we're on ordinal number 28. So let's say that our poll is going to start in the past a little bit so that it's still valid. And then it's going to end on ordinal 50. And then we're going to sign this message. So we're going to sign with the wallet. Pops up a Stargazer window here. There's no fee, of course, to sign, and it shows the data that I will be signing. Go ahead and approve that rather. And then we can click Create Poll. So this is going to take just a second here. There's a little bit of latency in that as the data kind of travels through the layers, but we should see our poll show up here in just a moment. Okay, so here we have our poll. With the name that I gave it, options 1 through 3. And then I want to kind of turn our attention a little bit to some of these links that we have here. So these are really important debug links for understanding what's going on the Metagraph. So just like before, how we looked at what the node info was for one of the nodes on our Metagraph, we can do the same things. We can contact one of those nodes and use the endpoints, the REST endpoints that it has defined. So we can take a look at the latest snapshot. So this is going to be the combined data associated with the most recent snapshot. So it'll have all the information about balances. If there are any balance changes that happened, you would see that update here, and other information about the snapshot itself. And then we can see this additional endpoint here, which is a custom endpoint that we created as part of the Metagraph. So let me just show it first. So it is just returning from calculated state within the Metagraph. It's returning a list of all polls that exist. We can see the name, the start and end ordinals that we set up, and then the results. So the options, no one's voted for anything just yet. And so if we wanted to check that out in the actual code base, we would look at modules. It's going to be L0, custom routes. Let's make this a little bit bigger here. But you can see that we have this get all polls endpoint. And you can investigate a little bit kind of how we're returning that data. But we also have a get poll by ID endpoint that we could use if we wanted to also. So just to kind of round out the example here, we can go ahead and cast our vote on this poll, which still should be open. Going to vote for option 2. And again, just sign with the wallet that we're voting for option 2 and cast the vote. So in this case, we signed with the same wallet as the creator of the poll. But of course, in a real example, you could use any wallet. You could vote on this. And you can see that option 2 is now winning with 100% of the vote. And, the voting power within this example is the number of tokens within the wallet. So whoever votes has the most tokens wins the vote. And that's what we're seeing here. So that's kind of all we're going to show with this example. Just a quick one to show you how you could set this up, explore, how this works, how Metagraph works with the front end, how you can use some custom endpoints to power a front end, and use that to create these on-chain applications with custom data types, and a lot of possibilities for what you could do with this, just starting with a simple example. Thanks.
So here's Marcus, full stack developer from Constellation. I will talk about two real case Metagraphs, DOR and Elpaca, that is already on Mainnet, Constellation. So let's start with the Door Metagraph. The Door Metagraph is a mainnet metagraph that validates IoT data from network of foot traffic sensors and distribute tokens rewards to network participants. So this metagraph, it's built to receive foot traffic data from the sensors, the DTM and F21 sensor that we have with devices, is a IoT use case where we receive those data, ingest the data on Metagraph, process those data, and then combine to the states, calculated in on-chain state that I will demonstrate later on the presentation. So for this Metagraph, we have two key actors right here. We have the datapreneurs that manage the sensor hardware, collecting the data for the network, and the node operators managing validator nodes, providing bandwidth and security for network. So right here we have the datapreneur that is the owner of the devices, the TTM and the F21s, and we also have the node operators that run the Metagraph nodes. We have some reward conditions on this Door Metagraph. That device should check-ins at least once per day in 24 hours, so once per day. Device is installed in a commercial location is another reward type. Like if your device made a check-in and is in the commercial place, it will be rewarded again because it's a different reward type. And we also have the third one where the user is signing up for a Door Analytics subscription. So if the user has this subscription, we have another kind of rewards.
And I should just say on the Door Metagraph use case, it's a really good example of a couple different things. One is how to ingest data from a external data source, in this case an IoT device, in a unusual format, right? So there's the Door sensors are sending their data in a binary format, and we're able to convert that into a format that the Metagraph can understand. And then just from a kind of full Metagraph kind of overview tokenomics perspective, Door is a really good example of how to incentivize different actors within a network using a token system. And so, ingesting data, the sort of creators of that data are rewarded in the datapreneurs, and then we're also rewarding the node operators that are keeping the network up. So just really good examples of a couple of interesting things there with this Metagraph.
Yes, the complete tokenomics of Door involves more complex stuff that if you want, you can take a look. Like since accumulating tokens should boost your reward, so we have more complex logical there that if you want to dive a little bit, you should see the logical there. So this is the data flow from the Metagraph. Like Alex mentioned, the DTM devices will send the data in a binary format. I will display how this data is sent later in the presentation. So the Metagraph will receive those data and will convert the binary data to the signed data update type. The function that does this is called a signed data entity encoder. This function will receive the raw data, process those data, and build the signed update, the data update type that we recognize and we process on Metagraph. So after receive this request, we send a request to the Door API. This Door API will store the data that we are receiving from the real devices, and then we'll send back to the Metagraph the account data. What is this account data? Like we need to know what address should we reward on the reward. So the Door API is the part that is responsible to send back to the Metagraph information of the user, such as the reward address. So with this information, we store the hashed data and account data, everything on chain. So I will describe a little bit more about this Door Metagraph later, but we receive the data, send back to the Door API, receive the data back, and with this enriched information, we will have the address that we should reward, that will boost reward, that we are staking, accumulating. So we have a lot of information returned from Door API that enriches our data. So before showing the Elpaca, let's dive a little bit in the code of this. So let me share the IntelliJ screen. Door Graph. Okay, cool. Here we have the Door Metagraph on the main branch, just like the GitHub repository. So everyone have access to this one. And let's start with the lifecycle flow. Right here we have this module called shared data. And on the main functions, we have the decoders. These decoders, we have the function called assigned data entity decoder. If we get the source of this function, we should see that is on the main functions, both on L1 and on L0. Oh, sorry, L0. Both mains we have the assigned data entity decoder, and I'm just calling this function right here from the lifecycle functions. So this decoder will receive a text plain. So the binary format is just a simple string, a binary string. Then I will convert this to a string, and then I will call this function that will get the string and build my byte array. So right here, I'm just basically building this byte array, and this byte array will be provided to this function that will build the signed data update type. That is the type that is returning right here, and is the type that Metagraph is process the data. This checking update is just an extension of data update. This is the custom update type from our Metagraph. So think on this like signed data update, but right here, checking update. When we are building the signed update, we receive from the Metagraph this binary that is encoded by CBOR, and CBOR is an encoder that you can search on the web. So right here we are using a library called Border. This library will decode this data and build this device check-in with signature. So right here I will have a CBOR field, hash field is the check-in hash, ID, and signature, because we need to validate the signature to check if it's valid or not. So ID and signature is important at this place because we need to validate if the data is valid or not. So once we have this, we build the ID and signature, just like I've described it, and then we build the signature proof function. The signature proof will be used to build the signed type. We will be to build these proofs that we will later provide it to the signed type. The CBOR field that we receive is another CBOR encoded, so it's double encoded. And this CBOR field, we are just printing right here on the logs to have control. But we will have this field right here later that will decode everything. But we will call the DOR API at this point. And if you can see right here, we will save the device check-in. We have like environment variables to have the DOR API URL. We are just calling the API right here, request post, and then we are parsing the response to build the DOR API response. This DOR API response is basically the reward address that I mentioned earlier, and information like if the device is installed, what is the location type, the billed amount monthly. So right here is the account information that we have mentioned earlier. Once we have this, sometimes the device does not exist on DOR yet, so that's the reason that we have a maybe right here, because it's not maybe the device is not registered yet on the API, so we have to handle those scenarios. Right here, like I mentioned, we have the CBOR, and we are just decoding again the CBOR to a hex, and then getting the information of the full traffic event, such like the events, the device timestamp, and the AC. The accelerometer information. So right here, we are just decoding the second CBOR to extract the full traffic information. Once we have this, we have enough information to build our check-in update type that we need the ID, signature, DTS, hash, and probably maybe the check-in DOR API. With this, we build the signed update date type. This is the return that we are expecting, and this is what we need to move with the validations. So returning to the main on data L1, we just received that information, and then we will call our first lifecycle function, call it validate update. This is the
yeah, Morgan, maybe we can kind of underline a few of the important concepts that you just covered there with the with that first method. So you know, this would be the first lifecycle method that is called after data is sent to the /data endpoint. And so the expectation of that endpoint is that all data will have a signature associated with it. And in this case, the request is coming from the DTM DOR sensor device. that device is able to sign the request, but it's not able to send it in a format like a JSON format that would be easy to ingest automatically for the Metagraph. It's sending it in this binary format with encoded through.
I have one example of the binary format right here. Like this is how it will look like the the request that we are receiving. Right here is all those binary formats, but this is exactly one kind of request that we receive on our Metagraph and we process. So this is the incoming request that we have has text plain, and then this is where we build the byte array and do all the process that I've mentioned it earlier. Go ahead, Alex.
Yep. So yeah, so this is an example of all the information that we need is in this binary format. Then this signed data entity decoder method is taking that, reformatting it into an internal data type that's wrapped in signed, and so we're able to then process that throughout the Metagraph code as a properly signed data update. So all that is important, and then of course this is the very first life cycle function that is being hit. So it's being used also to fetch external data and sort of enrich the data set with an external data source through the calls out to the data, so the Door API.
Yes. So let's move with the second lifecycle function, the validate update. This is the first validation that will happen on Metagraph. So right here, we can take a look at the validation that we are doing. Like first thing, we are validating if the check-in that we are receiving is greater than the limit timestamp. So sometimes the device can send we have energy drop or something like that, and then the device, when put again, can maybe send wrong data, like older timestamp or something like that. So the first thing that we validate, like if the checking that we are receiving is lower than the limit, so we reject. Right here, we can take a look that we are just validating, like I've mentioned it. We have this DTS and just checking. If this is true, we return this error, checking older than allowed. Second validation is if the check-in is lower than 1 day for the current date. We also check for older check-in again, but for just 1 day. It's different cases of older check-ins that we just check right here. And right here, we validate if the device is registered on our API. Like I've mentioned, we have devices that aren't registered yet on our API. So right here, we are just validating if the device is not registered yet. So we just drop this update, we reject, because we can't pay the reward for a device that not exists because we don't have the account information. So right here, we are just rejecting this. This combination of these functions using the product R is just combining the validations to see if we have any invalid from this, we reject the updates. All the validations should be true to move forward with the incoming update. After this, we do this initial validation. We need to serialize the update. We have the serializers and the serializers that are described a couple videos ago that we described individually, the serializers. But right here on Door, I will take a look on the serialized update because it's a little different. Like I've told, we have the check-in hash, and we are assigning the check-in hash. So right here on serialize, we need to provide the information that we signed. So at this case, we signed the hash information, the DTM check-in hash, and the signature is relative to this field. So we need to provide here the field that we are signing to validate if the signature is valid or not. Like, let's say that I will change right here, instead of update, I will provide the DTS. This will fail because we don't sign the DTS. We sign it. This will return invalid signature. We just signed this field. So we need to provide right here on this serialization the field that we signed it. So it's very important to provide right here exactly the object that you have signed it when you send the transaction, because the order will matter. Like if you are using JSON, the order of fields will matter. The uppercase, lowercase, all these details, it's really important so we can follow exactly the same pattern that we signed it. This is the validation of serialize. The other serialization is the same, like it's just a simple JSON. We described it in a few videos ago, like I've mentioned, so we can take a look at the videos to understand how the serialize process function works. After this, we will do the second validation. Remember, all the steps that I've talked right now until now is on the L1 layer. Right now, we will move to the L0 layer, the Metagraph L0. The validate data is the first function on the L0 layer. Let's move to the L0 layer, and right here we have the implementation of validate data. Is a validation, just like the validate update, but the difference here is that we are receiving the array of updates because we have a block of data transaction incoming. So we will validate the block of data transactions, and we also have the state. So right here we have how to validate our incoming data to the current state. Let's go right here. I'm just traversing the updates one by one to validate. Yeah, go ahead.
I guess, Marcus, the other important aspect of validate data is that this is running on the L0 layer versus the L1, right?
Yes, exactly. This is the first function that runs on L0 layer, the lifecycle function. This function right here, we have validations, just like the L1. We validate again some validations, but we also can check, like we can get the address from proofs. Like I've told, we are assigning the message and put on proofs, so we can retrieve our address directly from proof on our public key. And we can validate. We can do validations, like we can get on the state if the current check-in is greater than the last one, because it not makes sense. My device should move forward with the check-ins. Let's say that right here, I made a check-in today, and then I receive a new update from check-in yesterday, or I don't know, 1 hour ago. And I will go to my state and check, what was my last check-in from this device? Now. So if I receive NDTS lower than now, it's invalid, and I just reject right here. So this is a scenario. Yeah, go ahead, Alex.
Yeah, and I guess that concept is important for preventing duplicates within the consensus process, right?
Yes, exactly. Like, be sure to use validations to avoid duplication, because we have multiple nodes that can receive information and send that information over the consensus. So be sure to do the correct validations to avoid duplications.
Yeah, so the important aspect there is that there needs to be some sort of incrementing field that can be used in these validations so that you can detect if there are duplicates, and those will be rejected during the validation process. So in this case, it's just an incrementing timestamp, and so we can use that, the timestamp from the device. In other cases, it could be something like a last reference to the previous hash of the last update that was sent. That's something that is incrementing, and you can tell that whether there are duplicates or not is important.
Yeah, that's a good point. And we also recommend to take care with undeterministic fields, such as like when we are receiving date.now, as example. Now is relative. Like when one update received, we have one now, and then when other update income, we have a different now type. So dealing with undeterministic data, we need to take care to not mess. So once we validate the updates and the updates are valid, we need to update our states. And to update our states, we have this combine function. Right here, we are also receiving the updates, and we are receiving the state. This combine function can receive, like, this method is called even when you don't have updates, like every snapshot producing like time trigger snapshot at every minute that we have. This function is also called. So be sure to validate if we have updates. If we don't have updates and you want to do something like clearing old state or something like that, you can do it, because this function will be called all the snapshots. But right here, what we are doing is validating if we have updates. If we don't have updates, we just print a log saying that we don't have updates, and we return the state with empty on chain, and we keep our older calculated state. I will show a little bit the calculated state later, so you can see the structure of the state. But if we have updates, we will combine these updates to the current state. And then we have some field that is important for us on the combined functions, such as the epoch progress. This epoch progress is a field that comes from the snapshots, and this field is incremented at every minute. Every minute we have a new epoch progress. So it's like a counter that updates at every minute. And we use this field to pay the rewards on door, because the rewards should be paid once per day. So to avoid handling with multiple time zones and date issues, we use this epoch progress that helps us here. So
yeah, I think that's an important concept. Marcus, you had mentioned that you can't use something like date.now because it's non-deterministic. It could cause forking within your metagraph. So if you are looking to do something that's time-based, epoch progress is one of the main ways to do that. So it's a rough estimate of time, roughly one increment per minute. And so other implementations could look at the increasing ordinal number on snapshots, but those are processed as data comes in, and so it's not an even time-based measure, where epoch progress should be pretty close to about 1 per minute, or a little faster than that.
yes, ordinals can, like, we have two kind of snapshots, that we have time trigger and event trigger. So if your metagraph is producing a lot of snapshots, the ordinal numbers will increase a lot, and it's not deterministic to like 10 ordinals will be produced in a minute. So we can have 10 snapshots, we can have 100 snapshots. It will depend of your flow of updates. But cool, let's move forward. We have the epoch progress, and right here we also have the address from proofs. Again, like I've mentioned, we need the information of epoch progress and address. And right here we will call this combined device check-in. Roughly, this will get on the calculated state the address, the device information, and then we will get the Door API response. Right here we know that this response exists, so that's the reason that we are calling .get right here, because we validate previously on the validate data and validate update, like I've mentioned it. Then we will calculate the next reward epoch progress. So this function is just calculate the epoch progress that you should pay the rewards. You can take a look better right here at this code, that you will understand better this logic that we are calculating epoch progresses. But let's move forward. Right here, we also have the analytics bounding information. So this is another thing that we use on the calculated state to get the information about the bounty payment. Is a little different reward type that is described on tokenomics, how it works. So that's the reason that we have a separate for this. We have the proof of checking that we create this custom class just to have stored the proof. Oh, let me go back with the proof, and we have the checking state update. This is just the update that we want to put on chain. Right here, we can decide what we will put on chain. So we just put the device ID, is the ID that's signed in the message, the public key from the devices, the DTS, the proof, and the hash, like DTS, event, not the DTS, but event and AC maybe could be sensitive information, and we don't want to put this on chain. So we just want to put the hash right here, because we already stored this hash on our API. And if we want to retrieve and check the confirmation, we can use this hash to check on our API and see the values of events and the AC data. So I want to put on chain just this. So this is the information that will contain on the data blocks on chain on the snapshot.
And that's an example of kind of an important concept of notarizing data that's coming into the metagraph. So the full data comes in through the data endpoint, it makes it to this part in the life cycle, and then just the hash is what's being stored on chain. And so we have that ability to look at the chain data, get that hash. The hash isn't going to give any information about what the actual underlying data set was, but we can go back, taking the real data and compare it to the hash, and verify that that is the correct data for that hash. So it allows in the system for Door to retain control of that data through its API, while showing that it was ingested at that particular time. There is a history of it on chain, and it's part of the immutable snapshot chain. And so you kind of get both best of both worlds, where you're able to kind of control access to that data, even though there's a public record of it. And that's what's going on here in the code base.
Yes, exactly. So this is the on-chain state, and like I've mentioned, and then we need to provide the information of for calculated state, the state that will not be on-chain. So right here we are building this device info, and this device info is the information that we want to put off-chain. So right here we are starting the DTS, the Door API response, and here is interesting because the Door API response right here is not too heavy, but it can be a response that can be too heavy and exceed the limit of snapshot. So we are putting this information directly off-chain because this will not touch and will not increase the snapshot size. This state will not affect the snapshot size. We also put the information of the reward epoch progress, like when we should pay user, the next reward epoch progress. And this analytics bound information if users will receive that information. So right here, we just update the calculated state. And right here, we just update the on-chain state. Like this is just concatenating to existing ones. And we return right here the new state with the on-chain and calculated state updated that we made right here. The entire logical of the updates, the calculus epoch progresses is right here on GitHub, and you can take a look to get the details of how epoch progresses are calculated and that stuff. You can take a look right here. But let's move forward. After we call this, we will have inner function that will work to build a snapshot. And after we build the snapshot, it's important, like the on-chain state will be returned right here, and we will use this on-chain state with the other snapshots to reach the consensus and to select the majority, like the official snapshot, the majority snapshot. And after we're selecting the majority snapshots, we need to set the calculated state effectively in memory. This is one example that's using memory calculated state. So we have the functions regarding the calculated state, call it get calculated state, set calculated state, and hash calculated state. What we want to check right here is the set calculated state. This function will receive the snapshot ordinal and the state, the calculated state that you need to set. Right here, we are storing in memory, like I've mentioned. We are just using this ref to be an atomic update. So on the set function, we are getting the state ref, getting the current state, and then just concatenating the incoming state. Sorry, replacing the incoming state with the current one. So right here, we are building a new calculated state on this ordinal with the incoming calculated state. This function is going to be called after selecting the snapshot and the majority, because we need to decide, like we can have forks, like Alex mentioned it, for undeterministic data. So after selecting the official snapshot and not forking one, we will call this to set the official calculated state.
Yeah, just a note on that section. So those functions there are showing how to set the calculated state using in memory, which is the default. It's the easiest thing to use. We do have an example within the Metagraph examples codebase that it's our social sort of Twitter clone example, but that example shows how to use those same methods to use an external data store. So in that case, it's using a Postgres database instead of in memory. And so that concept can be extended. You can use any data store that you want. So if you're looking at a particularly large data set and you want to store a lot of data there, then maybe something different than in memory would make sense.
Yes, exactly. Cool. Besides that, I will mention, like we have a lot of serialized, deserialized, encoding, and decoder that this is just explaining on the other videos, and it's just the default, almost a default pattern. Like when encoding, decoding, we are using JSON for almost everything, but feel free to use your other encoders, decoders. I will just mention this hash calculated state because it's pretty important. This is the hash of your calculated state. So this function it's called during the process. And let's say that we have undeterministic data right here, like we are mentioning of data. If we call to hash calculated state with, like example, date.now, we will have one hash. But if we call the same hash calculated state with a different date, like you can have exactly the same state, but inside this state we have a field called date.now. All the other fields can be the same, but if we have only one field deterministic, the hash will be different, and this will return an error saying that we cannot update the state because it's an invalid state. because we have different hashes. The moment that we create the snapshots, the moment that we are validating, we will have two different hashes, and we will not combine because the hashes will not match due to the undeterministic data. So this is another point of attention to take a look when we are hashing the calculated state, to not use undeterministic data. Well, after this lifecycle functions, I think that I will mention two more. Right here we have this roads. That is not the lifecycle function by itself, but right here is where we can expose the custom roads that we built for our application. On Door, we have a pretty basic one that is just returning the calculated state, so we can have access of the calculated state directly on browser. This custom roads, we have a prefix of data application. It's all explained on the documentation and on the other videos, but think about, like, let's say that I'm running a local host. It should be something like localhost your port. Let's say it is 9,000 data application calculated state latest. This is one example of custom road with this prefix with the running host and port, and this is the road that I've just defined right here. When I call this on the Metagraph L0 layer, it will return for me the return of this function. That will just be my pure calculated state, because right here I'm just calling the getCalculated_state function right here. That's just returned my current state. So this is one simple example of exposing custom roads. We have more examples, like Alex mentioned on the Metagraph example, that have more elaborated custom roads that you can take a look. But this is a real simple one. And the second thing that I want to mention right here is not related directly with the data application part, but the rewards. We have the data application and rewards like overridable functions on the Metagraph L0. The data application is the data application part that I've just explained, and we have the second part of rewards that will be, it will be the function that will pay the reward for the user. Right here, I'm building my rewards as a service that I'm just starting this classes to work as a service right here, and I will just show briefly how the rewards work. Cool. This reward expects us to implement this function. This is a Lambda function that we are using right here, but it's implementing this distribute function that the output of this function is sorted set reward transaction. So the output of the reward should be a set of the reward transaction that we should pay. And right here, what we are doing is basically checking if we are having a snapshot created by event that we don't want to. We just want to check snapshots created by time, like every minute, like we mentioned it, of epoch progresses. If the snapshot was created by time, I will check if the calculated state exists, that we receive the calculated state as parameter of this function. If not exist, I can't pay anything because my information is on calculated state. But if exists, I will right here see, like, to checking the calculated state, I will see confirm. Sorry, let me just remember. This is just state. Oh, I'm just converting the data calculated state to checking calculated state. Data calculated state is the type of data that we are receiving, but we are handling a checking data calculated state that is just extending this function. So we are just converting right here. After convert, we will check if the users can receive the daily rewards. This daily rewards, we have validations right here to check if the epoch progress is the right one to pay. Like I mentioned, we have the next epoch progress on calculated state. And you can take a look better individually on this function that you should see that we validate if the epoch progress is the right one, and then we build the rewards. To build the rewards, like, we will just build, and at the end, we will return a sorted set of reward transactions. Right here, we have a straightforward logic. It's a little complex in talking about, like, we have a lot of functions, but it's pretty straightforward, the logic over here, because we just check if the epoch progress matches what we need to pay. If matches, I will calculate the amount that I should pay. Like, if I have staked $500, I will pay one amount. Like, it's all in tokenomics. That is what I want to say. You can take a look at the tokenomics to see the reward amounts. But right here, we are just basically checking the epoch progresses and paying if it matches the epoch progresses. Do you have any additions to this door, Alex?
Yeah, so maybe just kind of zooming out a little bit and looking at the whole system here, you sort of have two separate parts. One would be data ingestion, and so that's what we covered before. So data is submitted to the data endpoint, it runs through validations, it ends up in the combine function where part of that data is put on chain, and then part of that data is put into calculated state. And so at that point, the calculated state is where we're setting a future. In calculated state, we're setting a future epoch progress value that should be rewarded.
Yes.
And then within this rewards function, it's sort of operating separately, right? It runs every time there's a new snapshot. It's looking, okay, is this an epoch progress triggered or a time triggered snapshot? If it is, then we look at calculated state and see if any of the times that we previously set should be rewarded if they match with the current epoch progress. So it's kind of a two-part system where we're setting state in the first kind of ingestion stage and then using that state later for the rewards portion.
Yes, exactly. Like the rewards portion that I showed right here, it's available on currency Metagraph only, and on the data Metagraph. So this function is shared between both types of Metagraph. If your Metagraph is just for currency and you just want to pay rewards, you can use this function. You probably will not have the calculated state because it's from data. That's the reason that is optional. But you can customize your rewards logic right here. Cool. I think we can move to the other example. Let me share the screen again. Okay. Where it is. Yes. Cool. So recently we developed this new social metagraph, Elpaca metagraph. It's a social credit metagraph. It's designed to track the community activity within the ecosystem and reward positive behaviors with tokens. So this metagraph is a little different because it periodically fetches data about the network participation and applies meaning logic based on this data. The difference here is like different than an IoT example that we have devices send check-in all the time. This one, we don't have a physical device or a people send transactions. We have workers. Right here, we have cron workers that will be fired, that will be triggered at every defined interval, like 1 hour, 30 minutes, 2 hours, 1 day. You can define the interval. So when this interval reaches the end, we will trigger the worker, and this worker will fetch external APIs. And not external APIs, but you can do anything you want to the workers. Think like a Lambda function that you can do everything that you want. And then at the end of these workers, we are sending the updates to the Metagraph. So we are ingesting data to the Metagraph through the workers. And then the Metagraph will process this data, build the states, and pay the rewards according with the returning response from the workers. We also have one manual one. A manual one is just all wallets that we have should receive at least one Elpaca. And for new wallets, we will have a confirmation like this wallet is created or something like that. And then when the user confirms the existing of the wallet, we will send manually the update to the Metagraph, and we will pay the rewards for this wallet. But it's only one time per wallet. So we have validations that I will show up that rejects new updates for the same wallet. So the data flow of the Elpaca Metagraph. Like I've told, Metagraph has worker that fetch information from data source and send to the Metagraph. So workers will get the data from the data source. We call data sources right here. And these data sources can be one Exolink swap, one simplex transaction, posts on Twitter, X for future. We have this, and we get that information and return the requested data to the workers. Like with the data source, we'll fetch the data externally, process the information, return information for worker. Worker will build the update and send to the Metagraph. So worker will parse the the Elpaca will process the data and build a signed updates, exactly the signed data update type that we have on Door. Workers will self-sign the updates. This is important. Like to start a node, we need to provide the P12 file with the informations, the key of that node, and the worker will use that keys, the environment variables, to sign the message and send the message to the Metagraph. So it's self-signed. We will send the updates to the slash data endpoint, just like Alex has mentioned it. It's normal flow. We will send the information to the slash data endpoint. We will receive from both sources, workers and manual. We can have the manual update and we can have the workers update. And we will process the updates to update the state and distribute the rewards. I will show a little bit of the code right here. Just share.
Yeah, and while you're switching over, I think the interesting thing about this metagraph is that the metagraph is acting as both the collector of data, so it's reaching out into the world's different data sources, pulling all that data in. It's signing the data, so it's really the producer of that data, and then sending it through the normal data ingestion process through data endpoint, and it'll run through all the validations there. So a little bit different than the Door case where there's an external data producer. In this case, the metagraph is the collector of data itself.
Yes, exactly. So let's start right here on the L0. It's a little different right here than the Door because first thing, we externalize the lifecycle functions to be a service right here, not directly on main. It's exactly the same functions that Door have, but we just externalize to be a separate service. This is because the daemons, the workers, we call it daemons right here, it will be started as a resource. And we have this data application part right here where we can have the data application part, this Metagraph L0 service, just like I've mentioned it. But we also can start daemons. We can also start additional services. So this application also uses the pure config from Scala, where you can customize your application. Let me just show one example of configuration file to be clear. This application.conf, you can customize the configuration of your metagraph. Right here, we are providing, this is the data sources. And the data sources, external APIs, we need the URL key and the idle time that the worker should be triggered up. So this is the configuration of my application, of my workers individually. And I just show with this because you can take a look right here that I'm just loading the configuration. And to load this configuration, after this, we also need to build the key part to self-sign the message, like I mentioned it. And this implicit functions right here, we are calling because this function requires this implicitly this to work. So that's the reason that we have this implicit. But anyway, right here we build the configuration. We have the key pair. We have the calculated state service. We are building the service of calculated state right here. We have the workers. I will show in a bit how these workers are started. And we have the L0 service. My lifecycle functions depends of my calculated service. So I'm providing the service as parameter to my new service, receiving this right here. And then right here, I'm just calling exactly the same functions that I have on Door. You can take a look. That you should see that same lifecycle functions, same patterns using lifecycle function, exactly the same. Okay, let's focus on this daemon part that is that's different from Door. I have the service called Daemon APIs. Right here, I have the configuration that I've mentioned it when we have the key pair to self-sign the message. And right here, we have the daemons, the L1 and L0 daemons. The L1 daemons, if you go right here on the L1, is the same structure with service and main. Right here, we're spawning the L1 daemons. And on L0, we are spawning the L0 daemons. This is we decide the layer that we want that the daemons run. Right here, at this case, we use on L0 layer the daemons that should have access to the calculated state, because the calculated state is in memory of L0. So if we need the calculated state for something, you can spawn the daemons on the L0 layer. Okay, right here on the L0 daemons, we have the HTTP client that we just build right here to use. It's an HTTP4S client that we have on Scala to fetch the information. So right here we have the client. We have the publisher and we have the signer. The publisher will be responsible to send the message to the metagraph, and the signer, it will sign the message before publishing. It's the same publisher and signer. Like we use the publisher right here on signer. And let's say that I want to check this inflow transactions daemon. I will show, you can see that the structure of the daemons is exactly the same. The inflow, outflow, wallet creation, we receive the configuration. And then right here, we will build the fetcher. This fetcher, at this case, if you see right here, is the part of the worker that will fetch the information externally from API, just like we have right here, fetch transactions. Fetch the information externally using the HTTP client, build our class, and then build the updates. I will show building the updates in a bit. Let me just resume right here to not get lost. We will have the fetchers, we will have the processors, and this processor will just get the fetcher signer. So the process right here will get the update, the incoming update, sign the update, and publish the update. You see right here, we have the update. This update is right here, batch update is Elpaca update. Is data update type, just like Door. We are extending data update. Right here, we are calling Elpaca update, but it's extending this data update type. Oh, sorry, it's processor. Right here, we are receiving the updates, and we are checking the valid and invalid. So right here on the process, we are trying to send the updates like sign and publish, and then we will check what is success and what is the failures. Because let's say that I fetch an update externally and I need a reward address from DAG to pay the rewards. And let's say that the API return wrong DAG address. It's not the correct format. We have validations on the validate data and validate update that will check the consistency of this field. And if it's wrong, it will reject, returning a 500 or 400 or 400. And then it will return error for us, and we will put has a failure right here. The success update will proceed, and the failure updates will be rejected on the processor. Okay, we have this, and we have this spawn function that is shared, where we provide the processor, and we have the idle time. The idle time, like I showed on the configuration, is the time interval that you want your workers to be triggered. So let's say that I want my workers to run at every 10 minutes. I just need to go to my application conf, idle timeout. I can just type 10 minutes. This is a time finite type of Scala that it will works if we provide this syntax. Okay, let's return right here. The spawn is a function shared for all the daemons. And the processor will receive the fetcher, like I've mentioned it, and the processor is like, think about the processor that will do everything. Like processor will fetch the data, process the data, sign the data, and send the data to the metagraph. It will literally process all the stuff right here. Let me go back to the fetchers, like I've mentioned it, to not confuse. Fetchers will be defined functions that will be run on the processor. So at this scenario, my worker fetches information externally, build the data, and send to the metagraph. So I've built fetchers. Let's say that your data don't need to fetch externally. You can call a different name. You can call the name that you prefer to get the data that you want, process the data, and send to the metagraph. If you take a look right here, we have on shared data, daemons, fetcher, we have all data sources fetcher right here. From Exelix, I have one different type of transactions. For Simplex, I have another type of fetcher. For outflow, inflow, like it's all different. It will be variant according with what I want. At this case, I'm just fetching transactions. I will show the example of Exelix that I was showing. I will fetch the data, like I will receive the configuration. I will build the current date. I want to fetch the data from the current date. I will build the URL, like the API URL is just this one, like I mentioned, the API URL. Let's go back, Exelix fetcher. Yeah, exactly. we will build the URL with the endpoint transactions, the query parameters that Exolix expect us to have. With this, I will just print some information to control, and I will call the fetch transaction function right here with the URL. This will just fetch from the URL. I will provide the header of the authorization, the bearer token, and this client will convert the response into my Exolix API response. It will be an array of Exolix transactions. And this transactions is like ID, amount, coming from. This is the response from Exolix API. So if you take a look at the Exolix API, you should see that we have exactly this response, and we just parsing the data and get the information that we need to move forward and pay the rewards. Okay, once we have this, we will try to fetch. If we have errors, we will print a message saying that we have errors, and we will return an empty transaction, that we don't have any transactions due to this error. This print is just to have control on the logs, and you can take a look at your log and see I'm failing for this reason, then you can debug and maybe fix. It can be an API issue, can be credentials, it can be a lot of stuff that you can take a look right here. And we have a logical right here that we have this transactions to DAG. We will only pay rewards for when you swap on Exolix to the DAG coin. So we are just filtering from the response from the API the transaction that has switched to DAG. That's what we are doing right here. Then we filter this. Once we have this, we are just grouping for the withdrawal address. So let's say that my user made 3-4 withdrawals on the Exolix. So I just group by my address, my reward address, and build the transactions. So right here, I'm just building the transactions, the Exolix update type with my address and the transactions, the number of transactions. So if I have sent 10 transactions, I will have 10 transactions right here as my array. All these updates suffix at the end extends the Elpaca update. So this is all the updates types that the Elpaca supports. If you take a look at the fetchers, right here we have the Elpaca update, we have the Exolix update. On the inflow, we have the inflow update, outflow update the same, outflow update. So we are sending different types of update for each data source, and they are extending the same Elpaca update. So this we can use this way. When we receive these transactions, the publisher will send the informations. This publisher is just using the peer response class from Scala just to submit. We will submit the SIGNET update to the Metagraph, and the Metagraph will receive this data. Like, imagine this is you sending data to the /data endpoint, but instead of you, it's just a worker that is sending to you automatically. So this worker is just replicating human behavior of sending the data, but you can send a lot of data right here. We have a quick validation. Where it is, let me just, is on processor exactly. Yes, we have batches right here to avoid sending a lot of updates at once to the Metagraph. So let's say that I have 1,000 returns from an API. Instead of sending 1,000 updates to your Metagraph, that maybe this can slow down your Metagraph and lock your process, we have the concept of dividing, like splitting to batch sizes. We split in 100 updates. So we split into subarrays, and these subarrays will send 100 transactions. Then it will wait 10 seconds, and we will send more 100 and then more 100 until it reaches the total of updates. Do you have anything for this part, Alex?
No, I think that makes sense.
Yeah, no, it's a lot of information, it's a lot of details. I just want to focus right here on the Elpaca on this part, because the rest of the code, if you take a look on the lifecycle shared function, it's exactly the same. Like, we have the combined functions that will check if exist, if it will combine data. Here on the combine Elpaca update, we have a matcher from the update, so we can check and confirm what kind of update that we are handling. So if it's an Exolix update, we will have the combining from Exolix. If we have the receiving a simplex update, we will handling a simplex combine. So we have different combines from different update types. The code is pretty straightforward, so I think it's easier to understand. We have, after combined, we have this clean function. What is this clean function? Like I mentioned, we have all the wallets from Mainnet on this Metagraph. And let's say, like I've told, that we are receiving an update to pay the reward for a new wallet. So this clean will guarantee that this wallet has been paid and will be removed from the wallets to be paid. You can take a look detailedly at every clean function. At the end, it's just receiving data and clean updating the state. It's everything regarding the calculated state right here. The calculated state update is shared, like this response on chain. On this Metagraph, we are focusing more on the calculated state because it's where we have most part of the updates. The on-chain state right here, it will be basically the incoming update. So let's say that I received an update to pay inflow transactions. So my calculated state will be the payload that I received to the income transaction. It's not sensitive information. That's the reason that we are putting directly on the on-chain state. But again, you can customize your state the way that you prefer. This response right here, you can take a look that we are returning the on-chain and calculated state. And that's exactly what we are doing right here, just returning the on-chain state. I think, do you want to cover more points on this, Alex?
Maybe we could just take a look at the reward function. I know it's similar to Door, but it'd be good to cover.
Sure. Okay, main again, we have, again, the rewards function separate. And we have this make function. And this make function, let's go down. Yeah, trigger, the same thing. We are just aiming for time trigger. And this time trigger, again, we will get the current epoch progress. It will just confirm that this calculated state is from the Elpaca calculated state. If it's, we are calling this build rewards function, where we have the different types of rewards, like the inflow, outflow, fresh wallet. This is the data sources. And right here, we are getting this, and we are calling the shared function like this as an example. Right here, we are building the relation of address and amount. So from the XLX data source, we will check if the epoch progress is matching. If it's matching, we will pay for this address, this amount to reward. On the combined function that I've showed earlier on the XLX, we have the amount that we should pay right here. So it's basically what we are doing. We are just building the object, the calculated state. In this calculated state, we put the information of the amount that we need to pay. And on the rewards function, we are just getting this amount and building the relation of addresses and amounts to be paid. Once we have this combined addresses amount, is a map, and then we will use the fold on this map to build the transactions effectively, the sorted set reward transaction, exactly the output that we need. Once we have this built, we will pay for all this list that we return right here. The reward function right here is even more simple than Dora. Like, it's just getting the information, building the relation of addresses and the amount to pay, and that's it. I think that is worth to mention right here as well, the custom roads, because right here we have different roads. We have different data sources. So right here, instead of fetching the entire calculated state, we can fetch by individual data sources. So right here we have calculated state and data source name. We have a map of data sources. So we are getting calculated state by data source. We can return all at once if you want to, but at this case, we also can have individual calculated state. This function is basically just go to the calculated state and then get by the name that we have right here. It's pretty simple.
Maybe we could pull that up on the live Metagraph so people can see what that might look like.
What do you mean, like what Metagraph?
For the Elpaca Metagraph, we could see what these calculated state routes look like.
Oh, pulling. Okay, let me just check if I get exactly the URL. Okay, give me a minute. Okay, I have. Yes, I have. I just get the load balancer URL. Let me show.
And we can do a little cut.
Yeah. This is the response. Like we have the data application. This is the live metagraph on mainnet. And right here, you can fetch data application, calculated state, exoleaks. So this is our exoleaks calculated state. Right here, we have the reward address. We have the epoch progress that we should reward, the amount that we should pay, and the latest transactions IDs. This is used to avoid duplications. So user cannot be rewarded more than once per swap. So I cannot be rewarded by 35 Elpaca if I have the same update, the same swap in different days. So we validate to the older transactions right here. Yeah.
Yeah. So I think this is just good for people to know. So all of those different data sources have the calculated state available that you can go to the live metagraph, take a look at what those data structures look like and what information is being saved. And if you're pulling the project locally and running it, that's ways that you can kind of debug and get a view into what's happening as well.
This inflow transaction is the most recent one that we built from the bridge. So we are watching this and these addresses to every inflow transaction that this wallet is receiving. We have track right here. And when we have a new one, this array is empty right now, but because we clean to avoid duplication, like I mentioned it. But when we have new rewards, this object is built right here, and then we will pay rewards for these new addresses that send DAG for this to the bridge. Okay, I think that's it. I talked a lot of information.
Well, yeah, that's a good overview. I think that's great just to kind of dig into the production code bases a little bit. There's a lot there, so I think it's a good, it's a starting point for people to explore the code bases on your own. But yeah, thanks so much, Marcus, for walking us through all that.
Yeah, no problem. I know that there's a lot of information. It can let some of you guys confused, but feel free to reach us on the Discord channel on the stuff regarding the hackathon. We are here to help. Those two examples of Metagraph that I've showed you is live Metagraph is running right now. If you access the DAG Explorer mainnet, you should see that the snapshots are being produced. We are paying the rewards, and it's functional examples. So you can base on this because we are sure that they are working correctly.
Yep, and I think if you're just jumping in, starting with this video, you might check out some of the previous videos in the series. The last one was James giving us a walkthrough of kind of from scratch how to create a to-do kind of app. And that's a good starting point to understand some of the basics. And of course, the Metagraph examples repo, you can explore those more simple code bases and then dive into the production ones as well. So I guess happy coding, everybody. And yeah, like Marcus said, reach out on Discord or through other channels. Thanks so much.
Okay, thanks, bye.